So in the last video we have seen section 9 of APFI 77, that was for welding inspection. Now we'll go ahead with the metallurgy of welding in section 10. So some general requirements are given here. So in general, understanding of major principle is important to the inspector due to wide variety of base metals that are being joined by the welding during the repair of the equipment and significant impact on the material resulting from welding process. Structure of metal and alloys. Known of cast structure is important since the welding process is somewhat akin to making a casting. So basically welding is small casting, okay, in a foundry. Because of the similarity in shape of its grain, the weld can be considered as small casting. A solidified weld metal may have a structure that looks very much like a material that is casted. However, the thermal conditions that are experienced during welding product and cast structure with the characteristics of both beneficial and deleterious to unique of welding. Castings. Since the structure of the completed weld is akin to casting, it is important to review the nature of castings and overall arrangement of the grains and grain boundaries and phases present in the casting is called microstructure of the metal. So the cast structure, depending on the chemical composition, can exhibit a wide range of mechanical properties for several reasons. In general, it is desirable to keep the size of the grain small, which improves strength and toughness. So you will generally require a smaller grain size, but this is not always possible in the heat affected zone. This can be achieved by maximizing the cooling rate and minimizing the heat input. This increases the rate of crystal formation and decreases the time available for the crystal growth, which has a net effect of reducing the crystalline grain structure. Gases such as hydrogen can become entrapped when the metal is solidified and can also affect casting's integrity. In some cases, these gases create voids or porosity in the structure or can lead to cracking. Weldments are particularly prone to cracking because of trapped hydrogen. This problem can be avoided by carefully cleaning the weldments to remove all the hydrocarbon and moisture and use of low hydrogen electrodes, correct storage or baking of the electrodes, and the use of proper purging techniques with a high quality welding gas. Wrought materials. The majority of the metallic materials used for fabrication of refinery and chemical plants are used in a wrought form rather than cast form. Mechanical working of cast ingots produces a wrought material by process of rolling, forging, extrusion, which are normally performed at an elevated temperature. These processes result in microstructure that are uniform composition, smaller and more uniform grain shape. Weld metallurgy. So there are three parts of a weld: the weld metal, heat affected zone and the base metal. The metallurgy of each area is related to the composition of the base metal, weld metal and the welding process and the welding procedure that is used. Most typical weld metals are rapidly solidified, like structure of casting described earlier, usually modify in the same manner as casting and have a fine dendrite type of microstructure. Heat affected zone is adjacent to the welded area and is the portion of the base metal that has not been melted but whose mechanical properties or the microstructure have been altered by the heating of the weldment. So what happens is, when the weld area is heated, the area around the weld also heats. This heating of the area is generally beyond the recrystallization temperature of the metal, which leads the metal to change its grain structure. Okay. There is typically a change in grain size or grain structure and the hardness of the heat affected zone. The size or the width of the heat affected zone depends on the heat input used during welding. For carbon steel, heat affected zone includes those regions heated to greater than 730 degrees Celsius. Physical properties. The physical properties of a metal or alloy are those which are relatively insensitive to the structure and can be measured without the application of force. Examples of physical properties of a metal are melting temperature, thermal conductivity, electrical conductivity, coefficient of thermal expansion and density. So melting temperature, we don't need to understand it, but thermal conductivity. The thermal conductivity of a metal is a rate at which the heat is transmitted through the material by conduction or thermal transmittance. In general, the metals with high electrical conductivity also have high thermal conductivity. The metals with high thermal conductivity require added heat inputs because if the thermal conductivity high, it is going to lose the heat very fast. So you will require higher heat inputs so that the cooling rate can be controlled. So the steel may require a preheat. The steel is poor conductor of heat as compared with aluminium or copper. As a result, it takes less heat to melt steel. Aluminium is a good conductor of heat and has the ability to transfer heat efficiently. This ability of aluminium to transfer heat efficiently also makes it more difficult to weld at low temperature heat sources. Thermal conductivity of a material decreases, the temperature increases. Electrical conductivity. Aluminium and copper have high electrical conductivity as compared to iron and steel. Their electrical resistance is also much lower, and as a result, the less heat is generated in the process of carrying electrical current. This is one of the reasons that copper and aluminium are used in electrical wiring and cables. The ability of a steel to carry electrical current is much less efficient, and more heat is produced by its high measure of electrical resistance. Accordingly, steel can be heated with lower heat inputs than that required for aluminium copper because of its lower measure of electrical conductivity and high electrical resistance. Coefficient of thermal expansion, we already know when the metal is heated, the metal expands. When it cools down, it contracts. So how much it is able to expand is coefficient of thermal expansion. So metals with high coefficient of thermal expansion are more susceptible to wrapping and distortion during the welding. So basically what happens is, if you are welding something like this, if it has high coefficient of thermal expansion, it is going to bend like this. Okay. The increase in length and the shrinkage that accompanies heating and cooling of during welding should be anticipated, and the procedure established should ensure the proper tolerances are used to minimize the effects of thermal condition. Density, important factor employed during RT of weldments. The density of a material is important to the designer, but more important to the welder is the density of the shielding gas. The shielding gas has higher density. With a higher density has more efficient shielding gas than one with lower density, as it protects the weld environment longer before dispersion. Mechanical properties, these are more important for us. So examples of mechanical properties of metal and alloy are tensile strength, yield strength, ductility, hardness and toughness. Tensile strength, the tensile testing is used to determine the material's ultimate tensile strength, yield strength and elongation and reduction in the area. Tensile test is performed by pulling the test specimen to a failure with an increasing load. Stress is defined as force acting per unit area. The nominal stress of the metal is equal to the tensile strength. The ultimate tensile strength of the material is determined by dividing the external load applied by the cross section of the tensile specimen. Strain is basically change in cross section. So strain is defined as amount of deformation or change in shape that a specimen has experienced when stressed. Strain is expressed as length of elongation divided by the original length of the specimen prior to being stressed. If the stresses are removed prior to reaching, we already know this, in the stress strain diagram we already know that there is an elastic limit, the yield point, lower yield point, ultimate tensile strength. So if the stresses are removed prior to reaching the yield point, the material return back to its original condition. This is known as elastic deformation. However, if the material is stressed beyond this yield point, then a permanent change is going to happen. This is going to be called as plastic deformation. When the load is such that cracking starts to begin and the material fails, this is considered to be ultimate tensile strength. This is the last tensile strength that the material can sustain effectively. Beyond this, the material is going to break. Next is ductility. Ductility is stretching without failure. So in tensile testing, the ductility is defined as the ability of a material to deform plastically without fracturing, measured by elongation or reduction in area. This is usually expressed as the percentage of elongation within the 2 inches of the gauge length. The diameter at the point of fracture is also measured, and the reduction in the area from the original area is calculated. This reduction in area is expressed as the percentage, and both elongation and reduction in the area percentage are measured of material's ductility. The material that is subjected to load beyond its elastic limit becomes strain hardened or work hardened. Cracks and tears resulting from lack of ductility or discontinuities in a weld metal are evaluated for acceptance and rejections to the applicable code requirements. So this ductility can be identified by bend test. So when you bend the specimen, if your specimen is able to bend without breaking, then it is very ductile. But while bending, if the material breaks or if cracks are developed, then the material is not as much ductile and it will fail before bending. Okay, you understand this? Because if the material is more ductile, then if there is any foreseeable circumstances where the material is subjected to heavy loads, then the material is going to bend but not break. Okay, but if it's not ductile, it is brittle, and if it's brittle, instead of bending, it will break and your material would fail easily. Okay. Next is hardness. So hardness of the material can be defined by resistance to plastic deformation by indentation. Indentation hardness can be measured by various types of tests such as Brinell hardness test, Rockwell hardness test, Knoop hardness test, Vickers hardness test. Knoop hardness test is also known as micro hardness test. In alloys, the high hardness measurements could indicate the presence of untempered martensite in the weld or heat affected zone, while the low hardness may indicate the over tempered condition. A field test comparable to Brinell hardness test, commonly referred to as Tele-Brinell test, consisting of applying load on a 10 mm diameter hardened steel or tungsten carbide ball to a flat surface by striking the anvil on a Brinell device with a hammer. The impact is transmitted equally to the test bar and held within the device, known as Brinell hardness value, and through the impression of the ball. So basically you have a ball, you'll press that ball on the surface, you'll see an impression, you measure that impression, and you can identify Brinell hardness value out of it. The result is an indentation diameter in the test bar, in the test specimen surface. The diameter of the resulting impression are viewed using an optical comparator with a graduated scales and are directly related to the respective hardness of the test bar and test specimen. Again, Rockwell hardness test is also one type of hardness test. So in Rockwell hardness test, two loads are applied. One, a minor load is applied to reduce the effects of soil, dirt and localized hardness, and a major load is applied. So Rockwell hardness test, a minor load is always 10 kgs, but the major load can be 60, 100, 150 kgs. The indenter can be diamond coned indenters or hardened steel ball indenters of various diameters. The type of indenters and applied loads depend on the type of the material to be tested and as well as anticipated hardness values. The letter has been assigned to each combination of load and indenter. The scale is indicated by the suffix combination of H, H for hardness, R for Rockwell, and the letter indicating scale employed. For instance, the value 55 on the C scale is going to be represented as 55 HRC. H is hardness, R is Rockwell, and C is the C scale that is used. Because hardness test can also be done, again it will have a diamond shape indenter. So in-service hardness test may involve the use of portable variations of the above described methods. So generally basically a portable hardness tester is available. Alternatively, varying techniques based on rebound, indentation, resistance or comparator indentations can be measured, may be applied, and results related to the hardness scales are more commonly accepted. Whatever technique is employed may be accepted as long as it produces a verifiable and a consistent result. There is often in-service degradation requirements for the hardness related. For example, susceptibility to H2S cracking in the carbon steel is reduced if the hardness levels are maintained below HRC 22. Next is toughness. Toughness is basically defined as the amount of energy absorbed by a specimen while impact load is applied to it. So there are various testing that you can do. The most common is a notch toughness test, such as Charpy's impact test. So the toughness is the ability of a material to absorb energy and deform plastically before fracturing. An important material property to tank and pressure vessel designer is fracture toughness of the metal, which is defined as the ability to resist the fracture or crack propagation under stress. It is usually measured by energy absorbed in a notch impact test. There are several fracture tests available. One of the commonly known is a notch bar test known as Charpy's impact test. The materials are often tested at various temperatures to determine the ductile to brittle transition temperature. Many code standards require impact testing at or below the minimum design metal temperature based on service or location temperature to ensure the material has sufficient toughness to resist the brittle fracture. Preheating. The primary purpose for preheating the carbon steel or low alloy steel is to reduce the tendency of hydrogen-induced cracking. It does this by driving the moisture from the surface and slowing down the cooling rate, which helps prevent the formation of martensite. So basically, if you do preheat, you'll either eliminate martensite formation or you'll reduce the heat affected zone that you are getting because of the cooling rate that is slowed down. The preheating may be performed for n number of reasons. These reasons include to bring the temperature up to preheat and interpass temperature required by WPS, to reduce shrinkage stresses in the weld and base metal, which is especially important in welding joints with high restraint, to reduce the cooling rate to prevent hardening and reduction in ductility to the weld metal and the base metal and the heat affected zone, to maintain interpass temperature, to eliminate moisture from the weld area, and to meet the requirements of the applicable code such as BPVC codes. If preheat is specified in the WPS, it is important that the inspector confirms the required temperature has been maintained. This can be done by several methods, by using thermocouples, pyrometers, infrared temperature measuring devices, temperature indicating crayons. The inspector should remember that if the preheat is required during welding, the same preheat should be applied during tack welds, arc gouging, thermal cutting of the metal, all of which induce the temperature changes similar to the welding of the joint. The most important temperatures are preheat temperatures and interpass temperatures. Preheat can be applied using several different types of technique, but most common technique used in pipe and tank fabrication is electrical resistance coils or oxyacetylene or natural gas torch. Good practice is to uniformly heat the area on either side of the weld for a distance 3 times the width of the weld. Preheat should be applied and extended to at least 2 inches on either side of the weld to encompass the weld and the potential heat affected zone areas. The inspector should exercise caution when welding the metals of different chemistries to preheat requirements. Ensure that preheat on the both metals are in accordance with the code and the WPS documentation. Typically, the metal with the highest preheat requirement governs and will be identified on the welding procedure. Heat treatment. The purpose of heat treatment is to impart desirable mechanical properties to a steel that are appropriate for its intended service through microstructural changes, that is phase transformation. While there are many types of heat treatment based upon the material and its specific applications, the descriptions that follow are typically used across many industries. The heat treatments are achieved by bringing the metal to a transformation temperatures, usually 1700 to 1800 degrees Fahrenheit for steels, holding the temperature for a amount of time and then cooling down at various rates. There are various types of heat treatment. Annealing, material becomes more ductile in annealing. Normalizing, again material becomes more ductile in normalizing also. This method is carried out by relatively high temperatures when the material cause. So basically you'll heat the metal up at a higher temperature and you'll cool down slowly. So you'll either cool down in a furnace or you'll either cool down in hot sand, so that you can control the cooling down rate, which will give you enough time to readjust to ductile conditions or smaller grain sizes. This method is carried out at relatively high temperature, which causes the material grain structure to realign, resulting the structure has higher hardness and relatively high strength than full annealing. The ferrous material is heated to a temperature above the transformation temperature range, followed by cooling in still air to below the transformation temperature range. Unlike full annealing, the material is removed from furnace and air cooled. In annealing, the material is cooled in a furnace. In normalizing, it is cooled in still air. Next is hardening. Hardening is very easy. You'll heat the material and you'll rapidly cool it. So you'll heat the material, you'll dip it in some kind of oil or water so that it can be cooled very fast. Grain structure are going to be very high, but the hardness is also going to be very high, but the ductility is not so much. Ductility is going to be very less. So hardening or hardenability is defined as the property of the ferrous metal that determines the depth and the distribution of hardness induced by quenching. It is important to note that there is no relation between hardenability and hardness, which is resistance to indentation. Hardness primarily depends on the carbon content of the material, whereas hardenability is strongly affected by the presence of alloying elements such as chromium, molybdenum, vanadium, and to a lesser extent carbon content in alloying elements such as copper, nickel, and silicon. The cooling rate of the base metal can also affect by the section sizes of the base metal being welded, the temperature of the metal being welded, and the weld geometry. The simplest means to determine the hardenability is to measure the depth to which the piece of steel hardens by quenching from the elevated temperature. So basically this hardenability, or how much material can become hard, can be identified by Jomny test. So in Jomny test, you have a metal that is heated, and you'll have a water stream added from the bottom. While you have the water stream added from the bottom, you'll check that how much hardness distribution is there. If the material has very low hardenability, only this area would get hardened. If the material has very high hardenability, the entire section would get hardened. Okay. It may be important for the designer, welding engineer, and the inspector to understand the hardenability of the steel, as it can be indirect indicator of the weldability. Significant amount of martensite formation in the heat affected zone can lead to hydrogen assisted cracking or loss in ductility and toughness. Hardness in excess to those listed in the result in the stress corrosion cracking in the service due to the presence of sulfides in the process. A 200 BHN limit for carbon steel is equally as important as sulfur containing oils and is limited to chromium moly steel. So for carbon steel, these are the limits for hardness value. Okay, carbon steel 200, and for different, there are different values. Post-weld heat treatment, we already know what is a post-weld heat treatment. That is heating done after the welding to refine the grain structure and to remove hydrogen. So post-weld heat treatment produces both mechanical and metallurgical effects in carbon and low alloy steels. That varies widely depending on the composition of the steel, its past thermal history, the temperature and the duration of post-weld heat treatment, and the heating and cooling rates applied during post-weld heat treatment. Post-weld heat treatment requirements are generally governed by the construction code. So we'll talk about this very greatly, how to do it, what should be the holding temperature when we review the different kinds of construction code. The primary reason for post-weld heat treatment is to relieve residual stresses in the welded fabrication. In ferritic welds, post-weld heat treatment is also conducted to reduce the hardness of the heat affected zone. Stresses occur during the welding due to localized heating and severe temperature changes that occur. Post-weld heat treatment releases stresses by allowing the metal to creep slightly above the elevated temperature. However, there may also be in-service conditions that require particular post-weld heat treatment conditions. These may not be closely detailed in construction specification, and inspectors should therefore be particularly aware of these potential requirements when allowing, authorizing or inspecting the in-service repairs. So post-weld heat treatment is generally done to remove hydrogen, to change the grain structure, and to reduce the residual stresses that are developed when the metal cools down. Material test reports. There are two types of material test reports. On the material test reports, the heat analysis or mill certificate is a statement of chemical analysis, weight percentage of chemical elements present in an ingot or a billet. A product analysis is a statement of chemical analysis of the end product which is supplied by the manufacturer of the material. The product analysis is most useful to the inspector and engineer because it provides more reliable identification of the actual material being used for new fabrication, repair or existing equipment. So these are some details that are available in the material test reports. It is important to note that the material test report are not generally supplied to the purchaser unless requested. It is always a good practice for the purchaser to request the mill test reports. Weldability of the material. There are many books devoted to the weldability of the materials and alloy. Weldability is a complicated property that does not have universally accepted definitions. The term is widely interpreted by the individual experience. The American Welding Society defines weldability as the capacity of a material to be welded under the fabrication condition imposed into specific suitable design structure and to perform satisfactorily in intended service. The weldability is related to many factors, including the metallurgical compatibility of the metal or alloy being welded, which is related to the chemical composition, microstructure of the metal or alloy, and the weld filler metal used. The specific welding processes being used to join the metal, material, mechanical properties of the metal such as yield strength, tensile strength, ductility, toughness, the ability of the metal to be welded, such as completed weld that has sound mechanical properties, weld joint design, metallurgy and weldability. The primary factor affecting the weldability of the material and alloys is their chemical composition. The chemical composition not only controls the range of mechanical properties in carbon and alloy steel, it has most influence on the effects of welding of the material. The metal is said to have good weldability if the limits are narrow, and the metal is considered to have the poor weldability. Carbon content influences the susceptibility of the metal for delayed cracking and problems for hydrogen. The carbon content or carbon equivalent of the carbon steel determines the necessity for preheat and post-welding treatment. So the one tool that is developed to evaluate weldability of carbon and alloy steel is carbon equivalent concept. So this is carbon equivalent. So the percentage of carbon plus percentage of magnesium that is present in the metal divided by 6 plus percentage of chromium, molybdenum, vanadium divided by 5 and plus percentage of nickel and copper divided by 15. Once you solve all of this, you'll get carbon equivalent. If the carbon equivalent is less than 0.35, then it is readily weldable. That means no need for preheating or post-welding treatment. But if the carbon equivalent is greater than 0.35, then it will generally require preheating if the carbon equivalent is between 0.35 to 0.55. If it's greater than 0.55, then both preheat and post-weld heat treatment both are required. Okay. Weldability testing. One of the best means to determine the weldability of the metal or the combination of a metal is to perform direct weldability test. The simplest weldability tests are those that evaluate the strength and ductility of the weld. The tests that evaluate the strength include weld tension test, shear stress, and hardness. Ductility and fracture toughness include bend test and impact test. Weld restraint cracking specimens are designed to permit the quantitative variation in restraint under realistic welding conditions, so the contribution of the weld metal, base metal and the welding process can be evaluated with the respect to contribution to cracking. The typical weld restraint test method include lay restraint test, rigid restraint test and circular weld restraint test. These are various kinds of restraint tests that can be done. So these are different types of tests that can be done for weld cracking. Weldability of high alloys. Austenitic stainless steel. Austenitic stainless steel has a chromium content between 15 to 32% and nickel content between 8 to 37%. They are used for corrosion resistance and resistance to high temperature degradation. Austenitic stainless steel are considered to have good weldability and can be welded using common welding process or technique. The most common consideration for welding austenitic stainless steel are solidification cracking, hot cracking, distortion and maintaining corrosion resistance. The most common measure of weldability and susceptibility to hot cracking is ferrite number of weld metal. Austenitic welds require minimum amount of delta ferrite to resist cracking. Several sources recommend that 5% to 20% of ferrite content to prevent cracking. Distortion is most often a problem with welding austenitic stainless steel than carbon and low alloy steel. Distortion is basically changing of shape of metal after weld is cooled down. The thermal conductivity of the austenitic stainless steel is about 1/3 of that of carbon steel and the coefficient of thermal expansion is about 30 times greater. This means the distortion is greater for austenitic stainless steel than for carbon steel. More frequent tack welds may be necessary for stainless steel to limit shrinkage. The areas exposed to temperature between 430 degrees Celsius to 900 degrees Celsius for long enough time may precipitate chromium carbides at the grain boundaries. Using low carbon content stainless steel such as type 304L, 316L, L is low carbon, okay. So 304L, 316L or stabilized grades of stainless steel such as type 321 and 347 can prevent this type of phenomenon. It is also important to select proper filler metal to prevent the loss in corrosion resistance. Low carbon electrodes or stabilized grades of bare filler metal should be avoided. Nickel alloys. Nickel alloys such as alloy C276 and alloy 625 suffer from similar problem as austenitic stainless steel. If oscillation is not removed, a high convex weld contour will result, which will cause lack of sidewall fusion, weld undercut or slag inclusion. The formation of slight concave weld bead will be more resistant to centerline cracking. It is also important that the bevel angle for nickel alloys be wide enough to allow for this necessary oscillation of the weld torch. The wider weld bevel will also be beneficial with respect to weld preparation. Nickel alloys also suffer from a shallower weld penetration as compared to carbon steel or austenitic stainless steel. To overcome this, the weld joint has to be modified by a wider bevel and thinner root face. That is high depth to width ratio. The faster the nickel weld alloy solidifies, the less time it spends in the temperature range where it can tear. For this reason, preheating, which slows down the cooling rate of the weld, should actually be harmful, as it permits more opportunity for hot tearing to occur. So in this case, we would not do preheating. Okay. In austenitic stainless steel, the availability of the nickel alloys are also affected by the presence of high levels of low melting point elements such as sulfur, phosphorus, zinc, copper, lead. All of these contaminants can lead to cracking in either side of the weld or the base metal side. So this was all for section 10, which is metallurgy. You just have to read this once. It is very common when you talk about it, because all of these tests, the tests that are required, we are already doing in section 9 when we are doing WPS qualification. But this is the technical justification behind this. So this is the metallurgy that is involved when you are doing welding process. So in the next video, we'll see what are some problems associated with welding operation in refinery and petrochemical plant. Okay, so that's it for this video. Let's meet in the next video.